In this video, I'm going to be talking about reaction between an optically active carboxylic acid and alcohol. In this example, this here is the carboxylic acid, this one here, and that is because it contains the carboxylic group, and this one here is the alcohol, which contains the hydroxyl group. Now, when we talk about optical activity, what are we trying to say? If we look at this first compound here, this carbon has a hydrogen, a methyl group here, a methyl group, and of course the carboxyl group. Now this is 4 different groups, okay, which means that this carbon here is a chiral carbon, and of course because there is chirality, we say this compound is a chiral compound,
which makes it optically active.
And we go to this alcohol, same thing happened here. We have this hydroxyl group, we have an ethyl group, a methyl group, and hydrogen. 4 different molecules attached to this carbon. So this is also a chiral compound, and the chiral center is this carbon. So when 2 optically active compounds like this combine, what product are they going to give us? So for this particular one, when these 2 combine, they're going to be giving us an ester, and this reaction is called esterification reaction. Okay, and if you are asked to write the product without the mechanism, the fastest way to do that is to combine the OH from this and the H from the alcohol, remove it as water. So it's going to be giving off water. Okay, the other product will be water. So when you remove this, the next thing is to join this to this carbon. So there's going to be a carbon to oxygen bond, this carbon bonding to this oxygen when this has been removed. Okay, so the product we're going to be having would be this. So you see that the oxygen from the alcohol end has joined to the carbon of the carboxylic acid, the original carboxylic acid, giving away water. Okay, so this is going to be the product of the reaction, and this here is an ester, and that is esterification reaction. And because there's removal of water, this reaction can also be called
dehydration reaction.
Okay, now let's look at this product. We have this compound here, this carbon here, which also has 4 different groups. We have this carbon here, which also have 4 different groups. So this compound or the product that was formed now contains 2 chiral centers, and this product is optically active. Okay, so an optically active carboxylic acid, when they combine with an optically active alcohol, is going to give you an optically active ester. Okay, now let's look at the mechanism. So I'm going to be showing you how this reaction proceeds in case you are asked to draw the mechanism. Okay, so I'm just going to use strokes in this case to make it faster.
So before we start, remember this is the original reaction with the H2SO4 as the reagent. Let's go back to the mechanism. The first thing we do would be to protonate the oxygen and using the acid. Here I'm going to represent it as HF, H+.
So what you're going to have is this, okay? And there's a lone pair on this oxygen, which is going to pick up the hydrogen. So that's how the arrow will go the first time. And we're going to have this as the product of this step, which is O, H, and of course the hydrogen attached here. This oxygen is having 3 bonds, and of course, because this was used to pick up this, there's going to be a positive end here. Okay, All right, so at this point, this is where the alcohol comes in. So from here, you're going to have this plus the alcohol, which is OH, C, C2H5, and H. Now, what happens there is that this O
the lone pair
is going to then attack this carbon. Okay. Now, when it does attack this carbon, this double bond breaks. So it breaks, and the products we get from that step, which then look like this. Okay, so you're going to get an alkoxide. And of course, the oxygen, like that, the oxygen here is going to attach to that carbon. So that is what I have here. And of course, it has the OH still there, and then all the other components will also be there. So we have this C, this, okay? All right, and of course, the OH2 is still here. Now, this alkoxide is very unstable and tends to form back the double bond. So go back, we have 1, 2, 3, and 4. So this is going to form back the double bond, and then we have this leaving, because of course we can have this there because we'll be having more bonds than necessary. So this is going to break out, and then you have C to this, to hydrogen to C2H5. Then you have your double bond, and of course, since this has left, you can bring this up. Then you have O plus and the H, the C. So you can properly arrange all the molecules the way they should. And then this hydrogen shouldn't be here. Remember that there's a positive sign here. Okay. The oxygen here is having 3 bonds, so it's going to be positive. And also here, you carry it over to this place. Now, it's extra, so we need to remove this hydrogen. So there's going to be a removal of hydrogen. Okay. Remember, our water has left, so it's going to form the product that we can finally have, which is this. So removal of hydrogen, use that. Okay. So we have here, and oxygen is now on its own, and then we have this. So this is our product. So that's the steps you take when you are doing esterification reaction. This is a reaction mechanism, all the steps